Okay.
Equilibrium. So the question may arise, why did we study equilibrium first and kinetics last? Because kinetics is a harder topic. Well, understanding equilibrium, it works better if you have an idea about kinetics, because equilibrium on the atomic level is based upon kinetics. Equilibrium is a macroscopic expression of the overall reaction. And it makes a comment about, actually not just a comment, it quantifies concentrations of reactants and products at a time when they stop changing. When you put two or more reactants together, they'll do their thing, and then you'll usually have some reactants left over, and you'll watch the concentration, and the concentration of the reactants will stabilize with this much reactant and this much product. And at that point, you have reached equilibrium. What we have to understand is on the molecular level, activities are not static. The reaction that leads to products is taking place furiously, fast, but the return reaction from products to reactants is also occurring. And the balance between those two rates is what establishes equilibrium. Okay, so to sum this up, the macroscopic view is the reaction is static. As you've reached a point where you have a certain concentration of reactants left, and you have some product produced, and that doesn't change. That's what you see. That's what you can measure. But underneath, microscopically, the reaction is very dynamic. In other words, and we represent that with a double barbed arrow. Reactants over here yield products. So now, I may have mentioned this during chapter 12 discussions. But the reason that we study reactions at the very beginning is because there are reactants and no products. The reason that makes a difference is if you got products, then there's always a possibility of a competing return reaction. And we're interested in this part of the reaction here, that K, not the return reaction. So that's why we study initial rates for kinetics. Okay, so this is the way this reaction would look if we plot the concentrations over time. Right? Here's nitrogen, here's hydrogen. We start off with this much hydrogen, 3 times as much as nitrogen. And then they gradually decrease, of course. We learned that last chapter. The reactants decrease in concentration as we proceed, and the product increases. And we reach a point where they don't change anymore. That's the macroscopic view. And you may recognize this reaction. If I've discussed it before, it's the Haber process. We take atmospheric nitrogen and turn it into ammonia. It's called chemical fixation. And it's the source of, it was the source of explosives for Germany during World War I, because we cut off their supply of nitrates from Chile. Bird guano. So Haber set about the process of making ammonia from atmospheric nitrogen and any hydrogen source. And then you just oxidize the ammonia and make nitrates, and you're off to the races or off to war, whichever the case may be. Okay, So by definition, chemical equilibrium is that point in a reaction where concentrations of products and concentration of reactants become static. They don't change. And the reason for that is that the rate of the formation of products is now balanced by the rate return reaction of the formation of reactants from products. These two rates are equal now. So this rate here, rate of K minus 1, is now equal to the rate of K. Now, the K values for these reactions are more than likely different. Right? That's why you reach equilibrium when you, on some reactions where you have just a little bit of product, that's it. Or you may reach equilibrium when you have a whole lot of product and very little reactant left. So the rates are equal, but the Ks are still different. Those rate constants will be different. It's another way of looking at it. This is the forward rate of reaction, which decreases over time because, well, actually, the reaction rate decreases over time okay, I was thinking about zero first and second order. It decreases over time no matter what the order. But the decrease is dependent upon the initial concentration. The rate is dependent on the initial concentration only for zero order and second order. First order doesn't matter. But the rate still decreases over time. The forward rate and the reverse rate increases until they meet. And now they're equal. Reaction rates are equal for what we are establishing as equilibrium. So here's an example. In this reaction, where we take water and carbon monoxide and make hydrogen gas and carbon dioxide, is just a sample reaction. And we want to ask ourselves, suppose this reaction is now at equilibrium. In other words, you have some reactants and you have some product, and the reaction rate, the forward and the reverse reaction rates are now equal. So what if you do something to that reaction? Say you add water. Right? How does that affect the concentration of each of the chemicals in this reaction? This is sort of this is a prelude to Le Chatelier's principle. If you increase the number of water molecules, and there's still some carbon monoxide there, is that going to allow for a little more reaction to take place? It will, until the reverse rate, it balances it. So what you're doing is when you add this component, you're forcing the reaction that way to shift a little bit to the right until equilibrium is reestablished. Similarly with hydrogen, if you add more hydrogen, it'll go back the other direction. That just emphasizes the fact that this is a dynamic situation. If you do anything to change it, it's going to respond. Okay. Now, I mentioned earlier that equilibrium could be quantified, and that's based upon the law of mass action. It was proposed in the middle 19th century by a Norwegian chemist and his brother-in-law, Weg and Goldberg. They were trying to describe chemical reactions in terms of what they called affinities. And what they observed was that if they know the concentrations They knew when the reaction had reached equilibrium because they could measure the reactants and products that were left and found that they did not change. So they wanted a mathematical expression that would describe that condition. In those days, they called studies of reaction rates chemical dynamics. We call it kinetics now. And for when they reach this condition called equilibrium, we call equilibrium, they call that studying chemical statics. So it's true, dynamics is motion and statics is not motion. So there were changes taking place as long as the dynamics were operating. They noticed changes in concentrations initially, and then eventually they reached a condition called chemical statics that they call chemical statics and we call equilibrium. Right? No, don't do that. It's always on. It'll drain my batteries. Turn it off. Get stuck here. Now we work on. Maybe the batteries are getting low. Let me swap them and see if that works. Oh, yeah. I think it's good enough to get grades. Thanks. So, your decision. No, it's not gonna work. Okay, I'm gonna have to do without the pointer today. I have to use my finger. Let's see if this works. Okay, we're still scrolling through the slides. All right, so our generic equation might look like this. We have an A, the B, C, and D represent the reactants and products. And then these are the coefficients for the balanced equation. In equilibrium, you can write the expression. Unlike chemical kinetics, chemical equilibrium, you can write the expression for the law of mass action based upon a balanced equation. Now, of course, with chemical kinetics, when you have a mechanism, steps in an elementary step in a mechanism, you can write the kinetics expression for that step because we did it. But for the overall reaction, chemical kinetics is empirically determined. But law of mass action can be determined from the balanced equation. So in the numerator, for this K, this constant, which describes the equilibrium for that reaction, you have the concentration at equilibrium. That's what the square brackets mean. That's the concentration at equilibrium is raised to the power of its coefficient. And that's the same for the product. If you have two reactants, it would be the product of those two. Products. If you have two products, it will be the product of those two raised to the powers of their coefficients. If you have more, like E, F, G, it just expands the numerator. More terms to multiply in there and to take the powers of them. And then in the denominator, you put the reactants. Okay? Another important factor is the K value is always given without units of measure. And that's for practical reasons. If you have a complicated reaction with many reactants and different powers coefficients, which become the powers, then you can see that very quickly you can end up with an expression of unwieldy dimensions. In other words, the units of measure for K could be anything. So what we do is we're very careful to write the expression correctly. Here, balance the equation and write this expression correctly. And then when we calculate the value for K, we don't need the units of measure. In fact, if you look up units, if you look up K values for different reactions in reference manuals, you will never find units of measure. They're always reported without. The only thing that they would do is if there's a table of them, they'll say at the top, what are the units of concentration that go into this calculation? Because you can use molarity, which is more common. You can use partial pressures if everything is a gas. For instance, those two are very common. But the table will tell you the units of measure that were introduced into these terms. Okay, whether it's molarity or partial pressure or percent by volume or whatever the case may be. As long as you know that, then when you do your calculations, you can be careful to use the right units of measure for your terms as they go in. Then the K will work for those units of measure. Okay. So since our equilibrium constant is based upon a balanced equation, suppose you want to study the reaction in reverse. What effect does that have on the K value? Well, if you want to study the reaction in reverse, here's my pointer. Then look at it this way. I think it's better if I describe it. If we have an expression here, like this, for our generic equation, and K is then equal to big C to the C, little c power, big D to the little d power, divided by equilibrium concentration of A to its coefficient and B to its coefficient. And what happens if you reverse that reaction? Right? If you want to run it backwards, what happens to K? Well, now these become the products, right? Now they become the products. And the products become the reactants. So they go in the denominator. Right? So the K for this reaction and the K for this reaction are reciprocals of one another. You just flip it. So now this one is equal to 1 over the original K. In case you have to flip the equation, when would we want to do that? If we were using the Hess's law, combining equations, and we want to find out what's the K for the overall reaction after you add these reactions together. You need to know what to do with your Ks so that when you get your target reaction down here, you'll know what the K value is based upon the Ks for the individual reactions that were part of the calculation. Okay? What if you have to multiply this by a constant? Right? Let's say we have to multiply it by, we have to double it. Right? Sometimes we have to do that. Remember the trick when we balance equations, sometimes you can, as an intermediate step, you can use a fraction for your coefficient. And then you just get rid of the fraction to finish it off. Multiply by, lots of times it's so many halves. I remember one like 25 halves. So you multiply through by 2 and it gets rid of the fraction. So if you do that, what does that do to the K value? Well, what is this? 2A, 2A, 2B, 2C, 2D, correct? Okay, let's factor out that power, mathematically speaking. We can factor out the 2 and put it here. Right? That's correct, mathematical. You, I forget the proper term. You move this power as an outside term for the whole thing. So the K of this modification, if you multiply the whole reaction through by a power, then the new K becomes that power, that multiplier is the power of the new K. Okay, so in this case, K squared would be the new K. All right. What factor changes K for any given reaction? K is a constant for a given temperature. So when the K value is quoted, the temperature has to accompany it. Be somewhere in the discussion. Right? If the temperature changes, then the K will change. And it doesn't matter how much reactant or product you begin with, the K is a constant. It's an equilibrium constant. So you can start off with all reactants, or you can start off with all products. When it reaches equilibrium, the K will still be constant as long as the temperature didn't change. And that brings up the discussion of the difference between equilibrium constant and equilibrium position. The equilibrium constant is a ratio of concentrations of products over reactants. The equilibrium position could be any concentration. As long as that ratio gives you the K, then you're at an equilibrium position. So you could have tiny amounts of reactants and products give you that value of K, right? This is an intensity factor or an intensity property. Or you can have large amounts of reactants and products that will give you the same ratio, right? Two different equilibrium positions, but the same constant. And those equilibrium concentrations are extrinsic factors, capacity factors. Right? The amount of substance determines what they are. All right. Now, how is there are some Ks that are identified based upon the type of reaction that's being described. Typically, we say EQ for K is equilibrium constant of any kind, and it's usually in molarity units, KEQ. KW is a special one. It's reserved for water. Pure water, and we'll talk about this a little more when we get to acids and bases. Pure water will undergo a reaction with itself. And we can describe that in terms of equilibrium. Okay? That's where the pH scale comes from. We'll describe it later. But KW is specific for water. Ka is a constant that describes the equilibrium situation for an acid in aqueous solution. Right? And we'll talk about that in detail also. Solubility product, SP. is a K for solids that only partially dissolve in their solvent. And we can express that in terms of equilibrium. And formation constants are those reactions where you get an association of one reactant with another reactant to produce a strongly bound species of some kind that remains in solution. So that's a very special case. And then KPs are those where the units of concentration are in pressure. Could be atmospheres, could be pascals, whatever the case may be. All right, so here's one for, of course I have it. I don't know why this thing's messed up. It's forcing me to go out and buy a new one. The same reaction, the Haber process, occurs as a gas. There we go. And this is the balanced equation. One nitrogen molecule, 3 hydrogen molecules make 2 ammonia molecules. And the expression can be written in terms of either concentration units of, say, molarity or partial pressures. If we use partial pressures, we typically subscript a P. That identifies it as a pressure. So these two values, this K for some concentration units like molarity versus this case of P, will be different values because that concentration unit is vastly different from this partial pressure. So those Ks are not identical, but they are related. Let's use these values, equilibrium pressures at a certain temperature, right? So many atmospheres for the product, so many atmospheres left over for the reactants, and just do the calculation. So there's our partial pressures. When you do these calculations, don't forget the powers. I mean, I even make that mistake. You forget to do the powers, the coefficients in your reaction. And of course, that coefficient is 1. Okay, so when we do this calculation, we get this value, 3.9 times 10 to the 4th, is the equilibrium constant value in terms of atmospheric units of pressure for the Haber process at a given temperature. Now, it doesn't say what the temperature is, at least I don't think it did. At a certain temperature, right? So they're not telling us what the temperature is. But these two values are related. If you determine K for that reaction in molarity, you can apply the universal gas constant, temperature in Kelvin, and a change in the number of moles. And that calculation will give you the K, the Kp for that reaction. Right? Since the pressure is in units of atmospheres, we need this constant right here. And the temperature in Kelvin. Now, what's the delta N? How do you calculate the delta N? The delta N is the change in moles. It can be fractional, it can be positive, it can be negative. Right? So in this expression, right, we have this value for that we just calculated for Kp. We have the constant, we have the temperature, and we have the calculation of delta N. So the calculation of delta N is just like all deltas. Anytime you have a delta, it's final minus initial. So the final number of moles is 2. The initial number of moles is 4.
You're just having a time today.
Yeah. I need an assistant over here to click buttons for me. So the final number of moles is 2, right here. The initial number of moles is 3 plus 1 is 4. So that's where the delta N comes from. Final number minus initial number. Just like when we're doing thermal chemistry, right? Final temperature minus initial temperature. Final moles minus initial moles. And that calculation gives you a K of 2.5 times 10 to the 7th in units of concentration versus this value for units of partial pressure. Okay. Now we'll talk about reactions, equilibrium of reactions in terms of, in descriptive terms. In this reaction, all the reactants and products are gases. That's known as a homogeneous equilibrium. They're all in the same phase. This one would also be a homogeneous reaction. This is the dissociation of hydrocyanic acid into 1 proton in the cyanide ion in solution. Everything's in solution, that's homogeneous. So it's either the same physical phase, gas, liquid, solid, or in solution. This is a heterogeneous equilibrium. We have different phases. Right? You have a solid here, a solid there, and a gas there. We're decomposing potassium chloride to make potassium chloride an oxygen gas. Or in this case, you're taking liquid water and probably running a direct current through it and producing hydrogen gas and oxygen gas. That's a heterogeneous equilibrium. Now, the reason we're making a point of this is because the equilibrium expression changes for some heterogeneous equilibrium. And here's how it happens. I hope that's the next slide. Yes. When we write the expression, say we wrote the expression for this one, potassium chlorate yields potassium chloride plus oxygen. So we would normally say that K is equal to products to the powers divided by reactants to its power coefficient. But notice during a reaction, does the concentration change for a solid? Does the concentration of that solid change? No, it doesn't change at all. It's the same concentration. It's a solid. The concentration of the solid stays the same until it's all gone. Or it's produced here, and there's more of it, but it's still a solid. So solids and pure liquids like this in a different reaction disappear from the reaction, right? And all you're left with is this one, because it's the only one that changes during the reaction. Now, what happened to these terms? Well, you can say that we just converted them to 1 because their concentrations don't change. Or you can say we bury them in this K value. Right? So this is a different K than that one. Either way, it doesn't matter. What matters is they don't belong in the equilibrium expression. Solids and pure liquids disappear from the equilibrium expression simply because their concentrations do not change during the reaction. Okay. Now let's see, what can we gain what type of information can we gain from the equilibrium constant? Well, since it's written in terms of products divided by reactants, then if K is very large, the reaction is mostly products, right? The numerator is large, the denominator is small. So if K is very large, means this reaction goes way toward products. If it's very small, it's the other direction, because the denominator is large, the numerator is small. The products are small, reactants are large. Then if K is very small, we know that the reaction stays primarily as reactants. If it's in the neighborhood of 1, then we know that there's roughly an equal distribution. It's not exact because of all the powers and the multipliers and the concentrations, but we're speaking in general terms here. So if the value is near 1, we know that there's roughly even distribution of reactants and products left over at equilibrium. Okay. If the K is huge, that means it's virtually complete reaction toward products. And if it's extremely small, like 10 to the minus 10th or 10 to the minus 14th, then you can say that the reaction basically doesn't occur, for practical terms. Right? If the equilibrium lies to the right, the value of K is very large. If it lies to the left, the value of K is very small. Okay. Now, if it hadn't occurred to you already, what about describing a reaction at the beginning or somewhere in between on its way to equilibrium, but it hadn't got there yet? We could still write the expression, only it won't be for equilibrium. It'll be for somewhere in between. But it's useful to do this calculation because it tells you which way the reaction is going to go. Because you can compare the value that you determine for a reaction that's not at equilibrium to the K value for the equilibrium expression and compare those two values and say, all right, I know now which way the reaction is headed. It's either going to the right or it's going to the left. It's going to make more products or it's going to make more reactants. And that calculation is called the Q. So, for our generic reaction, the Q would have products and reactants. But instead of a square bracket, square brackets are reserved for equilibrium concentrations. We use parentheses. But we still use the same coefficients. Okay? So now, compare that to the equilibrium expression. They look identical, actually, except for the square brackets. Okay, now what can we say? If this value is equal to that value, that's the simplest case. If Q and K are equal, then we are at equilibrium. Okay? It's simple. What if Q is greater than K? Well, if Q is greater than K, that means we have more of this and less of that. So we have less reactant and more product, which means the reaction is going to the left, as written. Okay, you see that? Sort of. right? Let's write the reaction out. Okay. If this one is bigger than that one, what does that say? That says that products are more than they should be for equilibrium. You got more of this than you need for the equilibrium position. So if you got more than that than you need, which way is it going? It's going to have to go this way. Make a little bit less of that, a little bit more than that, until these come into balance. That's what I'm saying. The other possibility is Q is less than K. If Q is less than K, what does that say? That says that you don't have enough products yet. This is too small. This is too large, which means go to the right. So if Q is less than K, we're going to shift to the right. Here. I need a stick. If I'd known this was going to happen, I'd have a yardstick. Probably I'll bring a meter stick in here just for this occasion. Okay, that's what that means. Now, why do we want to do that anyway? Why don't we just let it go to equilibrium and then measure things? Well, maybe you want to know something about the reaction before it happens. Maybe you want to know if I mix this amount of A and B together, do I want to put some of that in there with them, or I just want to make reactants and just let it go? Or maybe I don't have any control over that. Maybe the situation demands that I have some of this and some of that. But I do want to know which way it's headed because I want to calculate where it's going to end up. Not this value because that's fixed. I want to know where it ends up in terms of equilibrium position. You know, how much of this is used up or how much of that is produced if I put that mixture together. And I'm going to show you how to do that in just a minute. But first we need to learn how to calculate the K value from actual real world values. Right? For this reaction, the iron 3+ ion is combined with this thiocyanate ion to produce iron thiocyanate. This is one of those drawn line. I'll probably think of it about the time I see it. Where is it? Formation constant. Complex ion. This is a complex ion that forms in solution when we put iron 3+ and thiocyanate together. You're going to do that next week. You're going to do this reaction. This produces a blood red or a brick red color. Very prominent. This in solution is kind of a yellow. When you put those two together, you get that formation, that complex ion that is easily detected. That's why we use it. So then we can speak in terms of, well, if you add more of this, or you add more of that, you get more blood red. I mean, it gets darker. But if you find some way to subtract one of these, then this will shift that way and it'll disappear and get lighter. So you can see it happen. Okay, but we want to know the equilibrium constant. All right. So these are the starting conditions. 6 molar iron 3+, 10 molar thiocyanate ion are mixed at some temperature. And at equilibrium, the concentration of this complex ion is 4 molar. It's easy to measure that. They probably do it spectrophotometrically. Right? They just did like we did, tune their spectrophotometer for a particular wavelength and measure its appearance. And if they calibrate it properly with known concentrations, then you can say exactly what the concentration of this is. What's the value of the equilibrium constant? Okay. Those are given amounts. Okay. What do we do with them? This is called an ICE table. Stands for Initial Change Equilibrium. ICE table. So initial concentrations, what are they? What's the change that occurs? That's why we need to know which way is the reaction going to move. Is it going to move to the right or to the left? Because the change is dictated by that movement. Right? And then now what's the equilibrium position? The equilibrium position is the one you use to calculate the K value, obviously. So our initial, and I like to set it up like this, where you have the reaction above the table. Like that. And then you form the complex ion. 2 plus. Notice you got 3 plus here, a minus there, 1 to 1 gives you a 2 plus. Right? So the charge is balanced. You got a 2 plus on the left and a 2 plus on the right. Okay, initially we start off with 6 molar, correct? Here, and 10 molar here. How much of that do you start off with? 0. That's right. These are easy to do. You don't even have to calculate the Q. You know that if there's none of this to begin with, which way the reaction is going. It's headed that way. Okay? This is an ICE table where you actually know part of the outcome. Right? It says you end up with this molarity of that at the end. Right? How did it get there? Well, the change is positive. We have 4 molar, right? Plus 4 molar of that. So how did that happen? Well, look at the ratio here. This is 1, this is 1, and this is 1. So if 4 molar showed up here, it had to come from here. And it had to come from here. Right? Conversion factor. 1 to 1 to 1. If you get 4 over here, then it had to be, you had to lose 4 from this side and 4 from this side. Okay? So now we can calculate the equilibrium concentrations. 4 from 10 is 6 molar. So we know that we have 6 molar thiocyanate there in solution, and we have 2 molar iron 3 plus ion. Now all we have to do is plug in our equilibrium expression. Right? We have product divided by iron 3 plus times thiocyanate. And only number 1 is the coefficient for each one is the power. So you put those together in that expression, you find the K is 0.333. Now that we know what K is, we can do some more interesting things with this ICE table. We can change the concentrations. Right? If we change the concentration here and here, then we can use that to calculate the equilibrium position because now we know the K. Okay? So in this case, we're going to start with 10 molar iron. Let's erase these because the situation changes. We're going to have a new equilibrium position. But does the constant change? No. It's at the same temperature. Right there. It says so. Same temperature. So the K does not change. But we're given 10 molar of this one to start with. And how about thiocyanate? 8 molar. Okay? How much of this do we have? 0 again. We're starting all over again at the same temperature. Okay. So what's going to change? Which way is it headed? That way. Right? So we're going to end up, we're going to add some of this. Right? That's our unknown. We're going to add some of that. Where is that coming from? Well, you're going to subtract some here and the same amount there. So what do we have here? We have 10 minus x. I'm going to leave the 0 out for space. And 8 minus x here. And x there. Right? So if we write our expression, we know what k is. It's 0.333. That's equal to this one divided by this one times that one. Okay? And then, see, am I attacking the right question? Yeah, we know. Oh, what's the concentration of this one? Right. So when you set up these ice tables, if at all possible, set up your unknown so the unknown value is the answer to the question. In this case, it is. Right? Concentration of iron thiocyanide is this answer. So once you solve for x, you've got your answer. There we go. Okay. So there's the table set up. It's a little more colorful than this one. And this is our expression. Now, you can probably see right off the problem. This is going to give you what? A quadratic. So you're going to end up with a quadratic equation in the end here. And if you solve the quadratic, right, what is it? Minus b plus or minus b squared minus 4ac divided by 2 times a, 2a. I've got it on my calculator. I think it's still here. No, it's not on this one. That's my phone. No, it's not on this calculator. All right, it's on a different calculator. So I wrote a little card and I pasted it to the back of my calculator. So if you have to use the quadratic, you need to know that expression. And that should be in useful information for you, just as a reminder. Sometimes you can get by without using the quadratic, using little tricks. But the problem is these x values. Well, this x value, because that one doesn't work. X can't be 1599, right? Because 1599 subtracted from these is nothing. It's a negative number. So you always get 2 answers, don't you, in a quadratic solution. So you have to decide which one is reasonable. And this one is 5. So x equals 5. All right. The trick, yeah.
I remember doing these in math when I had to take math in college, and I hate them.
You have to be very methodical about the solution.
I
yeah.
hate doing them.
So once we find 5 here, we can ask ourselves, what if 5 compared to 10? Is that a substantial amount of 10? Well, yeah, it is. And it's a substantial amount of x, so we can't ignore it. We've got to do it quadratic. There are some situations where the k value is so very, very small that the x is going to be so small you can ignore it. And in that case, we can keep this x and ignore that one and that one. And then the solution becomes simpler. And there's a rule that we follow. It's called the 5% rule. If the answer here, you take if you eliminate these two, do the calculation, and then you take the value that you get, and you plug it back in here, and here, and say, all right, what would that give me over here? All right, say that's your unknown now. So you plug your proposed x in here that you eliminated earlier, and you calculate what would the k be. And then you compare the k with the actual k and say, is it within 5% of that k? If it is, then you can go with that solution. If it's not, then there's another thing you can do, and I'll tell you about it later. It's called sequential iteration. Okay, so we know now that that value is 5. Under these circumstances, that's the equilibrium position. It's now 5 from that is what? 5, 5, 3, and 5 is the equilibrium position. Those are different concentrations than we found on that earlier problem. It's a different equilibrium position, but it's the same K. What about this reaction where you have 6 molar here and 6 molar here, and that K? It's the same type of solution. You just go through the problem, solve the quadratic. Now X is 3. Okay? All right. So these are general instructions for solving equilibrium problems. They have to be modified to suit the situation, but they're a good starting point. Always balance the equation. You cannot write an equilibrium expression without a balanced equation. That's first and foremost. Then you write the expression for equilibrium using that law of mass action. If you're talking equilibrium, you have to have that expression. Then what are the initial concentrations? Where are you starting from? Then, if necessary, calculate Q. When do you not need to calculate Q? When one of your reactants or products is 0. Right? If you have a reaction where one of the products is 0, then you know the reaction is headed that way. Or if you have plenty, you have items for reactants, you have values for reactants, and one of your product concentrations is missing, you know the reaction is going to the left. But if you're given concentrations for all of your terms in that expression, then you have to calculate Q to know which way is it headed. All right. Then you set up your ice table. Once you've defined the change that's needed, which direction is it going, then you look for the unknown value that will be closest to, and preferably will be exactly the answer that's to the question that's asked. Try to make X, the unknown, equal to the answer to the problem. It's not always possible, but when it is, it simplifies, it removes a step or two. If you have to choose X that's not the actual answer to the problem, all is not lost. Once you find that X, then you have to say, what's the relationship of this X to the answer? And make the conversion. Then once you've decided with your ice table, what is the expression for each of the equilibrium concentrations? And it'll have that unknown in it, that X value. Plug it in your equilibrium expression and solve it for the unknown. Okay? Sometimes the unknown is K. Sometimes if you know the K, you'll want to know one of the concentrations. Okay, so if we had time and energy, we'd solve each one of these, but it's solved the same way as the others. These are just different equilibrium positions because they have different starting concentrations. In this case, you do have a value for the complex ion for each one. So that means you've got to calculate Q to determine which way it's moving. And there are several examples of that in the review document to give you practice. I haven't handed that out yet. Nobody said it. It's a Monday. Let's see, here's the review document. I'll just hand them out in order that way. Beer in my hands. Back here. Here's work problems. Here. And this should be the slide. Good. And I might as well give you this one too. This is Le Chatelier's principle. That's the lab that we're going to do next week. Hopefully we'll have enough time to talk about it a little bit. In just a minute. All right. Ah, there it goes. It's back. Probably had to charge the capacitor. Okay. So back where we were, you have to calculate the Q for each one of these. And you just use these concentrations. You don't have to use any X's for the Q. You just use these, calculate the Q, and that tells you what direction the equilibrium is going to move. Okay, well, this slide has all the answers. But we got there by doing those calculations, finding out which way the reaction was moving, and setting up our X for the unknown. Okay, how about this one? A 2 mole sample of ammonia is introduced into a 1 liter container. At a certain temperature, the ammonia partially dissociates according to this equation. Is that balanced? Let's see. 1 nitrogen, 2 nitrogens. Nope, gotta balance it. So we need 2 ammonias, 1 nitrogen, and probably 3 hydrogens. Calculate the value of K if at equilibrium 1 mole of ammonia remains. Right? So let's set up our equation. This is the opposite of the Haber process. Right? We flip the equation. They're all gases. That's 3. And this is 2. And then we set up our ice table. Okay? Now, what are the initial conditions? A 2 mole sample of ammonia is introduced into a 1 liter container. What's the concentration of ammonia? 2 moles per liter. There it is right there. 2 molar. And no nitrogen and no hydrogen. So we know which way this thing is going. It's headed to the right. At equilibrium, we have 1 mole of ammonia remaining. Right? So we only have 1 mole per liter remaining. Correct? So if we have 1 mole remaining, how many disappeared? Minus 1 molar, right? That's the only way you can get there. So how many of these were added, right? If you subtract from this side, it's got to end up over there. So half of it ended up over here, 0.5 molar. And this one is actually a ratio of 3 to 2. So if this is 1, then 3 would be 1.5. Everybody see that? Now, what's the equilibrium? 0.5 molar here, 1.5 molar there. Now we can calculate the K. We just say, all right, K is equal to nitrogen to the first power, hydrogen to the third power, and ammonia to the second power. Now we can plug in our values. Equilibrium values. So this one is 0.5. This one is 1.5 cubed. And this one is 1 squared. Okay? So we need a calculator to finish this one off. So let's cube 1.5. 1.5 inner cube it. There. 3.375. That sound reasonable? Yeah, 3.375 for this one times 0.5 and then divided by 1. So I get 1.62 units. Let's carry it on out. Okay. Initial conditions, equilibrium conditions, rounded off to 1.69. Okay, that's our K value for this reaction. Everybody see how that was done? Any questions about that? That was a homogeneous equilibrium. Everything was in the gas phase. This is also homogeneous. Gas and gas. So, let me look at my hard copy. Let's see what's coming. I don't want to waste all our time. Let's see. Okay. It just gives the answers. So I need to show you how this one's done. So there's reactant. They're both gases, so I'm not going to write gas in there. This is 2 in 2. So initial change equilibrium. Initial concentration. 1 mole sample of N2O4 is placed in a 10-liter vessel. So initial concentration of N2O4 is 1 per 10, or 0.100. No. Yeah, 3 significant molar. Okay? And allowed to reach equilibrium. So what's this one to start with? 0. Correct? Allowed to reach equilibrium. Calculate their equilibrium concentrations. We know the K value. It's given to us. 4 times 10 to the minus 4. All right, so which way is it going? That way. So that means we're going to have, we're going to add, actually, equilibrium concentration of N2O4 and NO2. So let's just subtract X from this side. So what does that mean? That means this is 2X. So if we solve for X, it's going to give us the equilibrium concentration of this one, and then just twice that gives us this one. Right? Because this is 2X. Actually, that doesn't give us the equilibrium concentration of this one. I misspoke. 0.1 minus X. Subtract X from this one, that gives you the equilibrium concentration of that. But 2X does give us the concentration of nitrogen dioxide. All right, so we can write our expression. 4 times 10 to the minus 4. K equals 4 times 10 to the minus 4, and that's equal to NO2 squared divided by N2O4. Now we can plug in our values. 2X squared divided by 0.100 minus x to the first power. Okay, here's where we want to ask ourselves, how big is x relative to 0.1? Look at this value here. If this is really, really small, that means you don't have much of this, correct? If you don't have much of this, then x is also very small, which means we can probably ignore that. And that would simplify everything. So let's do that. Let's say this is approximately equal to, let's go ahead and square that. What's that, 4x squared? And we're going to let this one equal to 0.100. We're going to say x is so small, based upon this value, that it will not influence this value significantly. So now we can solve for x. We'll say 0.1 times this one is 4 times 10 to the minus 5. Right? A tenth of that, minus 5. And this is 4x squared. So we need to divide this by 4 and take the square root of it. Well, this divided by 4 is just 1 times 10 to the minus 5th, isn't it? And then we'll take the square root of that. 3.16 times 10 to the minus 3. 3.16 times 10 to the minus 3 equals x. So now this concentration becomes 0.1 minus that, which is essentially 0.1. But before I get this, this leaves my calculator, let me multiply by 2. So that's equal to 2 times this is the value of NO2. 6.32 times 10 to the minus 3 molar. And this one, just for kicks, let's say 0.1. Let's subtract that from it. All right. 9.68 times 9.68 times 10 to the minus 2 molar. Let's see if that agrees with what they're saying. 0.97, yeah. And 6.32. Okay, so they did the same type of calculation. Rather than solve a quadratic, we said, we're going to say that if that's so small, it doesn't matter. Not for this calculation. And what you can do then is take this value, plug it in here, this value, plug it in there, and see how close it comes to that. Let's do that. So we'll put this one right here, this one right there, and see if it's very close to that, within 5%. So 6.32, I need to square that one. So there's my square button. And then divide by this one. 4.13 times 10 to the minus 4. 10 to the minus 4 is the calculated value I get from these values here. Okay, is that within 5%? Right? What's 5% of 4? Add 5% to 4. So 4, 1.05 times that is 4.2. So this is less than 5% away from that value. Okay? We can get away with it by doing that. All right. Le Chatelier's principle. Who was Le Chatelier? What does his name sound like? I'm sorry? Frenchie. Yeah, he was a Frenchie, all right. Le Chatelier said that if your system is at equilibrium and you do anything to disturb it, it will respond to mitigate that disturbance. It will shift, the equilibrium will shift in a direction that will reduce the impact of that disturbance. So how can we disturb and the equilibrium reaction? You can change concentrations. We've already talked about that one a little earlier. Just add more of a reactant or add more of a product, or take away part of a product, take away part of a reactant. That's the way Haber does it. When they say N2 gas plus H2 gas, 3 of those, makes 2 ammonias. The efficiency of this reaction, even with the catalyst, is very low. It produces just a little bit of ammonia. So they siphon off part of that reaction mixture, and they run it through a cooling unit that's just cold enough to condense ammonia, but not hydrogen and nitrogen. Right? The boiling point for this one is much higher temperature than these two. So if you just cool it a little bit, the ammonia will drop out as a liquid. And then you take the gas and you just run it back through your reactor. And you just keep doing that over and over again. And after about 3 or 4 trips, you got your efficiency up over 15%, which is acceptable. Anyway, so that's how you modify this reaction so that it will continue to favor product, which is what you want. You remove product. So that's what we did. We removed product by condensation, and then the reaction shifted again to the right.
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We fill 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
Concentration. If the system is at equilibrium, then all you have to do is to disturb the system with concentration is to either add or subtract any of the reactants or products. If you subtract some ammonia, like I was talking about earlier, you shift the reaction over here. If I add any of these, either one of these, will shift the reaction to the right. Now, that also depends upon, is there any left of the other component? If you add nitrogen and there's no hydrogen left, it's not going to do anything. But if there is some hydrogen left and you add nitrogen, it'll shift to the right. And if I were a manufacturer, I wouldn't do this. Add ammonia and shift the reaction back the other direction. That would be kind of defeating the purpose. But it tells you what happens if the system malfunctions and you get a buildup of ammonia in your system, then it'll drive the reaction backwards and you start losing product. So that's the easiest one to understand.
This is MSJ Chem. In this video, I'll be looking at Le Chatelier's principle and temperature. Changes in temperature cause a change in the equilibrium position and in the value of the equilibrium constant Kc. Here we have the chemical equation for the Haber process. In the Haber process, nitrogen and hydrogen react together to form ammonia. The forward reaction of the Haber process is exothermic. This can be seen by the negative value for the change in enthalpy. If the forward reaction is exothermic, the reverse reaction is endothermic. We can see this by looking at the sign of the enthalpy change, which is positive. So when we use Le Chatelier's principle to predict in which direction the equilibrium position will shift, we need to know if the forward reaction is endothermic or exothermic. If the forward reaction is exothermic, the reverse reaction is endothermic, and vice versa. Next, we'll predict in which direction the equilibrium position will shift when the temperature is increased. When the temperature is increased, the equilibrium position will shift to the left, which is the reactant side. And the reason for this is that the system will absorb the extra heat, favoring the reverse reaction, because it is endothermic. When the temperature is increased, the reverse reaction will be favored because it absorbs heat. Therefore, the equilibrium position will shift to the left, in the endothermic direction. Next, we'll predict in which direction the equilibrium position will shift when the temperature is decreased. So when the temperature is decreased, the equilibrium position will shift to the right, which is the product side. And the reason for this is that the system will produce heat favoring the forward reaction because it is exothermic. When the temperature is decreased, the equilibrium position will shift in the exothermic direction, which is to the right. Next, we look at the effect of temperature on the value of the equilibrium constant Kc. So for an exothermic reaction, increasing the temperature shifts the equilibrium position to the left and decreases the value of the Kc. So as we saw in a previous slide, the forward reaction of the Haber process is exothermic. Here we have the equilibrium constant expression for the Haber process. When the equilibrium position shifts to the left, the value of the numerator decreases and the value of the denominator increases. Therefore, the value of the Kc decreases. So an increase in temperature for an exothermic reaction results in a decrease in the value of the Kc. For an endothermic reaction, increasing the temperature shifts the equilibrium position to the right and increases the value of the Kc. Here we have the reaction between hydrogen and carbon dioxide to produce water vapor and carbon monoxide. As we can see from the sign of the enthalpy change, the forward reaction is endothermic. And here we have the equilibrium constant expression for the reaction. When the equilibrium position shifts to the right, the value of the numerator increases and the value of the denominator decreases. Therefore, the value of the Kc increases. So for an endothermic reaction, an increase in temperature results in an increase in the value of the Kc. So let's end with a summary, starting first with exothermic reactions. When the temperature is increased, the equilibrium position shifts to the left and the value of the Kc decreases. And when the temperature is decreased, the equilibrium position shifts to the right and the value of the Kc increases. And finally, for endothermic reactions. When the temperature is increased, the equilibrium position shifts to the right and the value of the Kc increases. And when the temperature is decreased, the equilibrium position shifts to the left and the value of the Kc decreases.
Temperature. How does temperature affect a reaction? Well, K changes as the temperature changes. So the easiest way I've found to understand this, the K does change, but as far as Le Chatelier goes, the easiest way to understand temperature change is it an endothermic or an exothermic reaction? If delta H is negative, that means it's exothermic. And the heat is produced as a product. Okay? That's an exothermic reaction. So now that you've got heat as a component in the reaction, you can say, what happens if I increase the temperature? If you increase the temperature, you're adding heat, right? You're adding this component, which drives the reaction back that way. So exothermic reactions will favor reactants if you increase the temperature. Endothermics puts the delta H on the other side. Right? That's an endothermic reaction. Now it's a reactant. The heat is considered in our scenario as a reactant. And if you increase the temperature, you drive the reaction to the right. Okay? That's the easiest way to understand changes in temperature. The actual effect is the way it changes the K. And that's why I would have preferred for you to watch the video, because they go into more detail about how the temperature affects the K. But as a practical matter, this approach solves Le Chatelier type problems. Okay. And as it turns out, this reaction here is exothermic. So heat's on this side. So if you increase the temperature, you're going to drive the reaction back the wrong direction. But you need a certain amount of energy in there, we learned from last chapter, as activation energy. It has to be a certain temperature before the reaction will even go. So you increase the temperature, but you speed up the reaction with a catalyst. So that's how Haber did it. And the catalyst is dirt cheap. It's just very finely divided iron metal.
The pressure of a system can be changed by either adding or removing a reactant or product, or changing the volume of the reaction vessel. The first point has the effect of increasing the concentration of the reactants or products. The second point refers to Boyle's law. Boyle's law states that pressure and volume are inversely proportional at constant temperature. This can be written in equation form as P times V equals constant K. Changes in volume will affect the pressure of the reaction vessel. For example, if the volume of the reaction vessel is increased, the pressure will decrease. And if the volume of the reaction vessel is decreased, pressure will increase. It should be noted that changes in pressure only have an effect on the equilibrium position when there are different amounts of gaseous molecules in the reactants and products. So next we look at some examples. The reaction we'll look at is the Haber process, in which nitrogen and hydrogen react together to form ammonia. In this equation we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. This means on the reactant side we have more gaseous molecules, and on the product side we have fewer gaseous molecules. When the position of equilibrium shifts to the side with a fewer number of gaseous molecules, this results in a decrease in pressure. And when the position of equilibrium shifts towards the side with a greater number of gaseous molecules, this results in an increase in pressure. So when we make predictions about in which direction the position of equilibrium will shift for changes in pressure, we need to consider the number of gaseous molecules in the reactants and products. So in the next example, we'll predict in which direction the equilibrium position will shift when the pressure is increased. An increase in pressure shifts the equilibrium position to the right, which is the product side. So the equilibrium position will shift to the right because there are fewer gaseous molecules on the product side, which lowers the pressure. As we saw earlier, there are fewer gaseous molecules on the product side of the equation. When the pressure is increased, the equilibrium position shifts to the side with a fewer gaseous molecules, which has the effect of lowering the pressure of the system. Just like for changes in concentration, changes in pressure do not affect the value of the equilibrium constant Kc. In our next example, we'll predict in which direction the equilibrium position will shift when the pressure is decreased. When the pressure is decreased, the equilibrium position shifts to the left, which is the reactant side. So the equilibrium position will shift to the left because there are more gaseous molecules on the reactant side, which increases the pressure. Because we have more gaseous molecules on the reactant side, an increase in pressure will shift the equilibrium to the left. And once again, the value of the Kc does not change. In our last example, we'll look at changes in pressure when there are the same number of gaseous molecules in the reactants and products. So in this reaction, we have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So the position of equilibrium will not change because there are the same number of gaseous molecules on both sides of the equation. So if we have equal numbers of gaseous molecules in the reactants and products, changes in pressure have no effect on the position of equilibrium. So let's end with a summary. In this table, we have change to the system at equilibrium, change in equilibrium position, and change in the value of the Kc. When the pressure is increased, the equilibrium position shifts to the side with fewer gaseous molecules. When the pressure is decreased, the equilibrium position shifts to the side with more gaseous molecules. And changes in pressure when there's equal numbers of gaseous molecules in the reactants and products has no effect on the equilibrium position. And as we can see, the value of the Kc does not change when changes are made to the pressure of the system.
Okay, What do we do with pressure? Pressure depends upon gases. Pressure changes where liquids and solids are concerned, and aqueous solutions for that matter. Pressure has no effect. Pressure only has an effect on gas components in your reaction. So what you do is you look at the balance of moles. In a balanced equation, the balance of moles, in this case, you have 2 total moles on this side, and you have 4 total moles on that side. Okay? So in this case, if we increase the pressure, how? Let's say we have a reaction vessel here with a movable piston. Right? You got your reaction going on in there. Increasing the pressure means we decrease the volume. Right? Boyle's law. Just do that. So if you increase the pressure, the response of the system is to produce fewer moles total. So how does it produce fewer moles if we increase the pressure? Increasing the pressure favors product because it's fewer moles. If we decrease the pressure, it favors more moles, reactants, in this case. Now, where would changing the pressure not affect the reaction at all? I mentioned one earlier. If it's solid and liquids and no gases involved, no effect. But even if you do have gases, when would it not affect the position of the reaction? If you have equal moles on this side and equal moles to that side, the same number of moles of reactants and products, changing pressure will have no effect on the reaction equilibrium position. Okay? What's another way to increase pressure? Add an inert gas. Some component that's not part of the reaction and will not react with any of the reactants or products. If you do that, what happens to the reaction? Nothing. Because you're not increasing the concentration of either side for the system to respond. So adding an inert gas does nothing. Okay. So those are the 3 conditions that Chatelier's principle will operate under. Concentration change, temperature change, pressure change, and the conditions under which they can be assessed.